Exponential growth and decay models. The law of uninhibited growth of cells says the number n of cells in a culture after a time t has passed is given by this formula. N at t is equal to n sub 0 times e to the power k times t, where n0 is the initial number of cells, k is a constant, the rate of growth or decay. So now when k is a positive number, when the k is a positive number, then we have exponential growth. And when k is a negative number, then we have exponential decay. This formula is basically the same as the continuous interest, compounding interest continuously. We had just letters that it was P. We had that P at t is equal to P0 e to the power kt. That was the interest compounded continuously, and that's basically the same, except we have different letters. P or n is the final amount, P or n0 is the initial amount, k is the growth constant, and t is the time. So now we have example 1. A colony of bacteria. A colony of bacteria that grows according to the function n at t is equal 100 times e to the power 0.045 t. N at t is measured in grams. What is the initial amount of the bacteria? What is the growth rate? What is the population after 4 days? How long will it take for the population to reach 150 grams? What is the doubling time of the population? Okay, so the initial, let's do A, the initial amount. We know that the formula for exponential growth is n at t is equal to n0 e to the power kt. So my n0 is the coefficient by e, which is the initial amount, and 0 is 100. This is the initial amount. That's the initial amount. K is the coefficient factor or constant, in other words, the growth rate. So my K is the coefficient by T, which is 0.045 is the growth rate. It's the growth rate. And now we want to do B. What is the population after 4 days? So 4 days is the time. So we are using the formula n at t is equal to 100 times e to the power 0.045 times t is 4 days. And now we can punch everything on calculator. And we are getting that this amount is 119.72 grams. So what is the population after 4 days? After 4 days there were 150 19 grams of bacteria, because the population is measured in grams. Now we have C. How long will it take for the population to reach 150 grams? 150 grams. So we start with the formula, and the population, the final amount is 150 grams. So now we have that 150 is equal to 100 e to the power 0.045 t, and we need to solve for t. So first we divide by 100. We have 150 divided by 100 is equal to 100 e to 0.045 t over 100. This cancel out, 100 cancel out. This reduces to 1.5. 1.5 is equal to e to the power 0.045 t. Now we need to bring that t down, so we take log of both sides, and log you can take, I'm gonna take natural log. ln of 1.5 is equal to ln of e to the power 0.045 t. By the property of log, the exponent can goes in front, so we have ln 1.5 is equal to 0.045 t times ln e. And if you punch on calculator, or if you know the property that ln e is 1, this one is nothing else but 1. So we are getting that ln 1.5 is equal to 0.045 t. So now to solve for t, I need to divide both sides by 0.45. 0.045 divide by 0.45. So this cancel out. This cancel out. So my t is approximately equal to, we can just punch this on calculator to get the number ln 1.5 divided by, and we get 0.1. So how long does it take for the population to reach 150 grams? It takes approximately 9.01 days to reach the population to 150 grams. Now the question D. The question D is, what is the doubling time for the population? What is the doubling time for the population? So the initial amount must double. Doubling time is the initial amount double. So now we have D. My initial amount is 100. When I double this, I'm getting 200. So we have 200 is equal to 100 e to the power 0.45 t. And again we need to solve for t. So first we need to divide by 100. I have 200 divided by 100 e to 0.45 t over 100. This cancel out. This cancel out. This reduces to 2. 200 divided by 100 is 2, is equal to e to the power 0.045 t. Now we take logs. We can take ln ln2 is equal to ln e to the power 0.045t. By the property of log, I can bring down the exponent. So I have ln2 is equal to 0.045t times ln e. And we know that ln e is 1. So we have that ln2 is equal to 0.45t. Now we can divide by the coefficient by t by 0.45. So this cancel out, and my t is approximately, when we punch this on calculator, ln2 divided by 0.045, I'm getting that the t is approximately 15.4. So the doubling time is 15.4 days. The doubling time is 15.4 days. Example 2. The population of a colony of insects obeys the law of uninhibited growth. If n is the population of the colony and t is the time in days, express n as a function of t. b. If there are 500 insects initially and there are 1,200 after 1.5 days, what is the size of the colony after 4 days? And c. How long is it until there are 8,000 insects? So to do A, we need to use the formula of uninhabited growth, which is n at t is equal to n0 e to the power kt. Express n of the colony as a function of t. So that's the n as a function of t. Now we're gonna do B. And B we have if there are 500 insects initially and 1,200 after 1.5 days, then what is the size after 4 days? First we need to find that k, because what we have, if there are 500 initially, so that's my n0 is 500, and now I have the final amount, n is 1200 after t 1.5 days. So that all three pieces of information, if I plug it in, I can solve for k. Once I have k and the initial amount, I can find the size of the colony after 4 days. So first we need to find k. So we can plug it in as 1200 is equal to 500 e to the power k times t is 1.5. Now we can solve it as before. We divide by 500. So we have 1200 divided by 500 is equal to 500 e to the power k times 1.5 divided by 500. So 500 reduces, and this 1200 divided by 500 reduces to 2.4. 2.4 is equal to e to the power 1.5k. K times 1.5 is 1.5k. And now we would like to bring that exponent k down. In order to do it, I need to have logs. So I'm gonna take log of both sides. It can be any log, the answer should be the same. So this, I'm taking ln e to the power 1.5k. Now I'm bringing this down, so I have ln 2.4 is equal to 1.5k ln e. Ln e is 1 by the definition of log, or you can just punch on calculator to see that indeed ln e is 1. So we have that ln 2.4 is equal to 1.5k. Now to solve for k, we need to divide by 2.5, by 1.5. We divide by 1.5. So we have ln 2.4 divided by 1.5 is equal to 1.5k divided by 1.5. 1.5 cancel out, and we can use the calculator to get the approximate value of k. And the constant is 0.5836 and keeps going. So k is approximately 0.583645 and keeps going. So I'm gonna approximate to 3 decimal places. After that is 6, so I'm gonna round it up. 0.584 is my constant. So once we have the constant, now we can find the population. Now we have the constant, we can plug it into the original formula, and we can find the population size, because it says what is the size of the colony after 4 days with the initial amount of insects, and this 4 days we're gonna use it. So now we have the formula. So that's part B, continue. Part B keeps going. I still have my initial amount is 500 insects, and I just calculated my constant, growth constant, which is 0.584 after rounding up. So they ask us what's the population n at t, and we have 500 and after t 4 days is equal to e to the power 0.584 times 4 days. And we can punch everything on calculator. And I'm getting 5,169. My n is approximately 5,169.8972, and keeps going. So that's the number of insects. So I'm gonna round it to the whole insect, which is gonna be 5,170 insects. There are about 5,170 insects. And now we need to find C. How long is it until there are 8,000 insects? 8,000. So we have C. We had the we have the formula, then n at t is equal to n0 e to the power kt. My n0 is still 500. K we calculated is 0.584, and now they ask us to find the t until there are 8,000, so n final amount is 8,000 insects. Okay, so we can plug it into the equation. N at t or n is exactly the same. So we have 8,000 is equal to 500 e to the power 0.584 times t. We divide by 500. To cancel this, excuse me. So we have 8,000 divided by 500 reduces to 16. So we have 16 is equal to e to the power 0.584 t. As before, we can take log, natural log. So we have ln of 16 is equal to ln e to the power 0.584 t. By the property of log, the exponent can go in front. Okay, so we have ln 16 is equal to 0.584 ln e. Ln e as usual is 1, and t, I missed the t. So I have ln 16 is equal to 0.584 t, and we're gonna divide by the coefficient by t. 0.584, 0.584. This reduces. Okay, so we are getting ln 16 divided by 0.584, and we are getting that t is approximately 4.7475 and so on. So I will approximate this t as approximately 4.7 days. How long is it until there are 8,000 insects? It takes 4.7 days to get the colony to 8,000 insects. Now we have next thing that we would like to talk is radioactive decay. Radioactive decay is given by the model A at t is A0 e to the power kt. The model is exactly the same. We have the same as n at t. Now I'm using A. So n0 e to the power kt. And for decay, we said before that k must be negative. Then we have decay. So we can use n, we can use A. Any letters is good. So half-life of a radioactive substance is the time required for half of the radioactive substance to decay. Half-life is that half of the radioactive substance decay. So we have example. The half-life of a radioactive substance is 2,700 years. If 10 grams are present now, how much will be present in 60 years? So first we need to find the constant K. We have that model that A is equal to A0 e to the power kt. We need to find K first using the half-life information. Okay? Half-life means that the initial amount is half, so the final amount A is equal to 1/2 of the initial amount. Or you can go that A0 is 100 and then would be 50, or choose any letter, 1 and 1 0.5. For T, this half-life is 2,700 years. So if I plug it in to my equation, I'm getting 1/2 A0. My A is 1/2 of A0 is equal to A0 e to the power K times 2,700. Now we can divide both sides by A0. So this A0 cancel out. And I'm gonna write 1/2 in decimal, that is 0.5. It's equal to e to the power, I multiply, so it's 2,700K. Now we wanna bring that K down, so I need to take log of both sides. ln 0.5 is equal to ln e to the power 2,700K. By the property of log, the exponent can go in front. So we have ln 0.5 is equal to 2,700K ln E. Ln E is 1. And now we can divide both sides by 2,700. By 2,700. So this cancel out, and my K is negative. K must be negative, of course. So my K is negative 0.000256721. I'm gonna keep the long, so then I have good approximation. Several digits. Okay, the constant must be small because it decays very slowly. If you have substance, half of the substance remains after 2,700 years, so the decay is very slow. So now, if 10 grams is present now, how much will be present after 60 years? So we start with the formula that A is equal to A0 e to the power kt. Now my A0 is the initial amount is 10 grams, and T is 60 years. And I'm gonna use the constant K, 0.000256721. I want to have pretty good approximation, that's why I'm using negative, of course, right? Negative. So now, how much will there be? We have that A is equal to 10 e to the power negative 0.000256721 times 60 years. We can use the answer key, 10 times e to the power times 60, and I'm getting 9.8 is approximately 9.847 grams. After 60 years, we still have 9.8 grams from the substance of 10 grams, and that makes sense because half would go, 10 grams would go to half in 2700 years, and now we have just 60 years. So after 60 years, there are 9.847 grams of the radioactive substance. Now we would like to talk about Newton's law of cooling. Newton's law of cooling says the temperature U of a heated object at a given time can be modeled by the function U at T is equal to T plus U0 minus T e to the power KT. K is negative because we are cooling down, it's going down, and T is the constant temperature of the surrounding area, U0 is the initial temperature of the heated object, and K is a negative constant. So now we have example. An object is heated to 100 Celsius and is then allowed to cool in a room whose air temperature is 25 degrees Celsius. If the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees? Determine the elapsed time before the temperature of the object is 40 degrees. So we will use the Newton's law of cooling. And as before, probably we need to find the constant first. So my T is the room temperature. My T, so we have U at T is equal to T plus U0 minus T e to the power KT. T is the room temperature of the surrounding area, so T is 25 Celsius. If the temperature of an object is 80 degrees after 5 minutes, so that 80 degrees is my U after 5 minutes, and an object is heated, initial is 100, so U0 is 100 Celsius. Now from this information we need to find the constant, so my U is 80 after T is 5 minutes. So from those pieces of information we need to find K. Substitute everything to the formula and we get U is 80 is equal to T is 25 plus U0 is 100 minus T is 25 e to the power K times time is 5. Okay, so now we can work this out. We can bring this 25 over, so I have 80 minus 25 is equal to 100 minus 25 is 75. So we have 75 e to the power 5k. 80 minus 25 is 55, is equal to 75 e to the power 5k. Of course, we cannot add this 25 together because this number is bounded by multiplication. First you need to multiply. So we can only bring this over and calculate that together. Now we need to solve first for e before we take logs. It needs to be clear exponent. So I'm gonna divide both sides by 75. Divide by 75. This cancel out. So we have 55 divided by 75. So I'm getting 0.7333 is equal e to the power 5k. Now I can take log of both sides. I can take log of both sides. ln of 0.7333 is equal to ln e to the power 5k. By the property of logs, that 5k can go down exponent. So we have ln 0.7333 is equal to 5k ln e. Ln e is 1, so we can divide by 5. We can divide by 5. So my k is I'm using the answer key for this approximation. So I have log of my answer divided by 5. I'm getting that this is minus 0.06203 and so on. So I'm gonna keep it as approximately negative 0.062. Okay, and now once we have k, we can find once we have k, we can find what is the when will its temperature be 50 degrees. So we need to find time t. Okay, so we have the same formula. We have initial amount and the temperature of the room is the same. So now we are asking that when u is 50, what is my t? Using my k that we calculated minus 0.062. Okay, so we can plug it in and find this. U is 50 is equal to t is 25 plus u0 is 100 minus t is 25. E to the power k is minus 0.062 and t, we would like to find the t. So 25, we can bring this over. So we have 50 minus 25 is equal to 100 minus 25 is 75. E to the power minus 0.062 t. 50 minus 25 is 25 is equal to 75 e to the power minus 0.62 t. We can divide by 75. We can divide by 75. Then this cancel out and we have 25 divided by 75 is 0.333. I'm gonna keep it and then I will use the answer key. Okay, So this one is approximately 333 is equal to e to minus 0.062t. We can take log of both sides. ln of 0.333 is equal to ln of e to the power minus 0.62t. By the property of log, this exponent goes in front. Is equal to minus 0.062t ln e. This is 1, so we just divide by minus 0.062 minus 0.062, and I'm gonna use the answer key for that approximation. So we have ln divided by negative 0.062, and that gives me 17. So my t is approximately equal to 17.719 and so on. So 17.7, and we have in minutes, 17.7 minutes. So the question was, when will the temperature of the object be 50 degrees? It will take after 17.7 minutes. The temperature of the object will be 50 degrees. Okay, and now we have B. Determine the elapsed time before the temperature of the object is 40 degrees. So the same situation. We have the formula U at T is equal to T plus U0 minus T e to the power kt. Okay, so now we have that T was 25 degrees, initial temperature was 100 Celsius, and we had that the constant K is minus 0.062, and determine the time elapsed before the temperature of the object is 40 degrees. So let's say that my final temperature is 40, and I'm looking for time t. So plug it in. And we get U, which is U at T is 40, is equal to T is 25, plus U0 is 100, minus T is 25, e to the power minus 0.062T. So this we will bring over, and I will 40 minus 25 gives me, we have 40 minus 25 is equal to 75 e to the power minus 0.62t. So 40 minus 25 is 15, 75 e to minus 0.062t, divide by 75. So this gives me 0.2 is equal, this cancel out, e to minus 0.62t. We can take log ln 0.2 is equal to ln e to minus 0.062t. Bring this over, bring the exponent down. By the property of log, we can bring the exponent down. So we have ln 0.2 is equal to minus 0.062 t ln e. We know that ln e is 1, so we can divide by minus 0.62 minus 0.062. Then this cancel out. And the time is approximately 25.958 minutes. So basically, roughly speaking, time is approximately 26 minutes. So it will take 26 minutes before the object reach the temperature 40 degrees.